My name is Genise, and I'm going to be presenting our paper, Gadget-Based Trapdoors on iNTRU lattices, and this is for the Indocrypt 2020 conference. So this is the paper, Gadget-Based Trapdoors on iNTRU lattices for Indocrypt 2020. Again, my name is Genise, and this is with my co-author, Baiyu. So I'm going to give a brief history of the Hash+Sign lattice-based digital signatures. I'd like to mention that there is a fruitful line of work based on the Fiat-Schmier heuristic and lattice-based signatures, but for us, the Hash+Sign paradigm is all we need to talk about today. So in 1996, iTide discovers a worst case to average case reduction for lattice problems, and this reduction, it states that it gives a random class of lattices such that when you pick one of these lattices at random, if you can find a somewhat short vector on average, where the randomness is over the choice of lattice, then you can find somewhat short vectors in any lattice for some fixed dimension n. It's important to note that this parameter n is going to be our roughly our security parameter throughout the rest of the presentation. So in 1997, GGH, they give a lattice-based Hash+Sign digital signature scheme. And even though this scheme isn't reducible to the SIS problem, the ideas and the underlying technique propagate through the Hash+Sign lattice-based schemes afterwards. In 2003, the iNTRU authors introduced a perturbation technique in a scheme they call iNTRU-Sign. And this technique, it's very important because it's later adapted to digital signatures based on discrete Gaussian sampling. And our work is going to rely heavily on this this evolved version of this perturbation technique. So in 2006, Gwen and Regev, they break iNTRU-Sign and GGH. And the idea is that each signature leaks information about the trapdoor. So in 2008, GPV remedies the situation by giving a Hash+Sign digital signature scheme that's based on SIS, and they're also able to prove that each signature statistically hides the trapdoor, and the way they do this is through a technique called discrete Gaussian sampling. And all of our algorithms presented in this paper are based on discrete Gaussian sampling, or versions of discrete Gaussian sampling restricted to a special class of lattices. So in 2010, Piker gives a discrete Gaussian version of iNTRU-Sign's perturbation technique. We call these discrete Gaussian convolutions. In 2012, Chancho and Piker, they give a gadget-based optimization of the GPV technique, and here they're able to efficiently break the Hash+Sign sampling technique into an offline and online phase, and the algorithms that we're going to present today are going to be this MP12 technique to a iNTRU family of lattices. And then, so in 2014, Ducal, Lubashevsky, and Prest, they instantiate this GPV, discrete Gaussian sampling technique over iNTRU lattices. And this gives a very efficient Hash+Sign digital signature scheme based on discrete Gaussian sampling. This scheme later evolves into the Falcon digital signature scheme, which is in the third round of the NIST post-quantum standardization. I'd like to mention, though, that this scheme does not use the perturbation technique, nor is it a gadget-based optimization, or it doesn't have this offline and online separate sampling stages. Okay, so now I'm going to give some technical background. If we're thinking about a lattice scheme, we should always have a good picture in our mind. And the reason is because we're working with Euclidean space. So to review, a lattice lambda is a discrete additive subgroup of Euclidean space, say Rm, and to instantiate this Hash+Sign trapdoor or this digital signature scheme, say that we're given a hash function from a message space to the integer cosets of the lattice. Let's just assume that this lattice is full rank, so its dimensions fill the whole space, and also that this lattice is integral. That means it has integer entries. Now, to sign a message, we first hash it to some coset, and then, using some trapdoor information, we're going to want to sample a short coset representative. And the reason we want to do this is that you can efficiently check a vector's length, Euclidean length, and you can also efficiently check whether a vector is in the correct coset or not. So if we would draw the picture, say this coset U, it has infinitely many coset representatives, but we're going to want to use some trapdoor information to sample a short coset representative, kind of in this fuzzy ball here of radius r. Okay, so how does this look, or what is the short integer solution problem? So now we're going to be working over this structured version. That means the matrices are going to be structured. So just a quick parameter soup up here in the upper right hand corner. Q is going to be some modulus. It's going to be a small polynomial in our security parameter n. And notice that this is much smaller than the modulus or moduli used, say, in elliptic curves or RSA-based cryptography. M here is going to be the rank of our module. It's going to be just some log of Q. You can think of this as log base 2 for now. And then we're going to work with polynomials, integer polynomials modulo some monic polynomial f. And really, our scheme is going to be doing this modulo Q. So we're going to be doing this over the ring of coefficients of these polynomials with coefficients modulo Q. Okay, so the short integer solution problem, or the inhomogeneous version, is say we're given a random structured matrix A here, which we can just think of as a vector over the polynomial ring, and the target T. Really, this target T is going to be the hash of our message. You want to find a short vector over the polynomial such that when you take this inner product, mod Q, you get the target back. Okay, so what does this look like? You're given this this random matrix A, the structured matrix, or this vector of polynomials, it's equivalent. And then you're also given this target mod T, and you have to find a short vector that maps to this target. Okay, a quick overview of discrete Gaussian sampling. A discrete Gaussian distribution over a lattice is more or less a continuous Gaussian distribution over the span of the lattice, but it's conditioned on being in the lattice or a lattice coset. So for our application, let T be this polynomial mod Q, which is the hash of the message. Then each signature is going to be in the following lattice coset. Now for simplicity, you can think of just T equals to 0 here, and then you'll see that this lambda of A is a full rank lattice in Euclidean space. And for us, we're going to be working over the cosets of this lattice. Now, discrete Gaussian sampling, oftentimes we denote efficiently sampling from this distribution as sampling over this D here. And S is, you can think of just as the width of the vector that this, or the average width that's going to produce. It's really the covariance of the continuous Gaussian scaled by 2 pi. And oftentimes So that if you don't see another entry here, that means that this distribution is centered at 0. But it's equivalent to sampling a zero-center distribution over a coset to sampling a non-zero distribution, non-zero-centered distribution. So for applications, what we really need is we need S to be wide enough such that the discrete Gaussian behaves like a continuous Gaussian, or that we say that it's smooth. And when this phenomenon happens, we can show that the signatures statistically hide the trapdoor. But there's a trade-off here, because the larger the S is, the higher the bandwidth is that we're sending across the channel when we send our digital signatures. Okay, so what is a SIS trapdoor? A trapdoor is really any information that allows us to efficiently invert this SIS function on this vector A. So in applications, we're going to generate this A together with the trapdoor. Note that this is not a function inverse. There are many pre-images for each target that we want. And like it's intuitively, this is going to be a randomized process, because really we're going to be using this trapdoor to sample a discrete Gaussian distribution over short cosets. Again, this little picture, same as before, but now we're going to be using this trapdoor information to sample this vector x. Okay, so now to apply this GPV paradigm for signatures, let's have the trapdoor be the signing key, and this matrix A be the verification key. Now, as I've been hinting at, to hash and sign, we're going to hash this to a polynomial t, and then the signature is going to be a discrete Gaussian sample over the coset defined by t, and this signature is just going to be this discrete Gaussian sample. So you can efficiently check that x is short and that the inner product is the hash of the message. Now it's important to note here that, again, each signature statistically hides the trapdoor. Okay. Now, I mentioned that MP12 reduces this to there's something that we'd like to call gadget-based, and now I'm going to define what these gadget matrices are. Now, these gadget matrices, they're really any matrix that where it is easy to solve the SIS problem on. So they're not randomized; they're fixed. Also, in our schemes, everyone knows what they are. So let K be this log-based B of Q, and then this gadget is just going to be this power of B matrix. And really, this matrix is just a vector with scalars as entries, so from 1 to B to the K minus 1. And for simplicity, you can often think of this B as just being 2. Now, given a coefficient modulo Q, you can take this coefficient and give its B-area expansion as a vector. And really what this does is it solves the SIS problem on this gadget. Okay. Yeah, and if you repeat this n times or on each of the polynomial's coefficients, then you can solve this on the whole SIS matrix when you just represent it as this gadget. Now, really, what we're going to be doing is we're doing a discrete Gaussian version of this. Okay, so now I'm going to talk about the MP12 gadget-based discrete Gaussian sampling technique. Now, say we have a structured version of this matrix A here, where you have a truly random A prime, And then the other part of A is the gadget shifted by this A prime times R. Here R is going to serve as the trapdoor, and it's going to be a matrix which has polynomials which have small random coefficients. And we call R a G-Trapdoor because when you multiply A times R, with I on the bottom, you get back the gadget. And what this allows you to do, it allows you to first take a sample X here on the correct coset of G. So if you have, say, the target is the hash of the message, and you take a discrete Gaussian sample over this coset based on G, which is easy, which everyone can do, you can then use the trapdoor to map this to a coset on the coset defined by the verification key, here A. And in the real scheme, we have to add a perturbation to statistically hide the trapdoor. Okay, so in 2019, this technique was extended to something which we're going to call approximate G-Trapdoors, or just approximate lattice trapdoors in general. And the point of the paper in 2019 by myself, Eli Chen, and Parentier is that we can save a constant amount of public key memory and bandwidth on the signatures or signature size if we just have some small error in the range of the SIS function. So you would hash the message to a target, and then instead of checking equality, you would just check that this pre-image is close in, say, Euclidean distance from the target, or say maybe L1 norm, whatever we need. Okay, now I'm going to talk about the iNTRU assumption, the iNTRU assumption, and then the contributions in our paper. So the iNTRU assumption, introduced by Hofstein, Pfeiffer, and Silverman in 1996, is the following. If you let LF here and LG be sets of polynomials with small coefficients, then the assumption is that this distribution on the left is computationally indistinguishable from a truly random polynomial. And this distribution, it's taken by sampling a random G, and then this G is not the gadget. It's just I'm just using this G so we stay consistent with the iNTRU literature. And if you take a random F such that F is invertible mod Q, then G times F inverse mod Q is pseudo-random. Okay, now also in 2019, in a paper with Baiyu and Genshi, Halevi, and Machancho, we introduce the iNTRU assumption, which is an inhomogeneous version of iNTRU. Now, here, G is the gadget. E is a random vector with small entries, and R is also a random vector with small entries, such that it's invertible mod Q. And the assumption is that this shifted version of E by the gadget times the inverse of R mod Q is going to be pseudo-random. Okay. Now just some observations. If you recall, a G-Trapdoor is any matrix that when you map to multiply by it on A, you get the gadget G. You'll notice that this short element R here is almost a G-Trapdoor in the case of iNTRU. So what that means is that if you just multiply each entry here by this polynomial R mod Q, you get the gadget plus some small error. Okay, so in our paper we give two two trapdoors, or two, say, like digital signature schemes. And the first one, it's an exact version of this MP12 technique, where we have the public matrix A here be this iNTRU matrix in something in what we call the HNF form. And then we can use this simple matrix here, given by the trapdoor, which is or given by E and R to form the trapdoor. And then it has small entries, and it also is exact, so it kind of like corrects the error introduced by E. So the advantages of this scheme, the secret key is roughly half the size of the secret key in MP12 for a fixed ring and modulus. We give a novel analysis in showing that the pre-image statistically hides the trapdoor. This uses a technique introduced in PKC 2020 where we frame discrete Gaussian convolutions as linear transformations on discrete Gaussians. And then also we provide an efficient implementation using the Palisade lattice cryptography library. Okay, now in this second contribution we have, we introduce a new family of approximate trapdoors on these iNTRU lattices. Now really we just use that this polynomial R with small entries is an approximate trapdoor for G. And the way you do that, it's the same as in the MP12 case. You can first sample a discrete Gaussian X over the G lattice that maps to the right coset, and then you return this scalar times the vector, and you'll notice that this is almost in the right coset, because here X is small. Now some contributions. To summarize the contributions, the advantage of this, again, we have a much smaller trapdoor size, and so maybe by a factor of almost 2 compared to MP12 for fixed ring and modulus. We also have a complete ring level parallelism here, and you can see this because you would first sample this discrete Gaussian X, and you would multiply in parallel by this vector R with short entries. And of course, we would have a perturbation here. Now, a technical challenge of this technique is that for reasons we show in the paper, this has a leakage both in the domain and the range of the SIS function. So we give a novel analysis on how to convolve these discrete Gaussians in the domain and range. And the way we do that is we also perturb the coset here, the hash here. And again, that's okay because we are using approximate trapdoors. So as long as the coset represented by the signature is close in range to the coset represented by the message, we would still count that as a valid signature. Okay, and then we also give an efficient implementation in Palisade. Okay, speaking of which, here is a table summarizing our implementation. Algorithm 2 is the approximate trapdoor, and algorithm 4 is the exact trapdoor. And we compare it to the paper with myself and Eli and Kretge in Asiacrypt 2019. And you can see that the timings are very favorable. So in this first column here, this is just a toy example that the security isn't high enough. But in these other columns here, you can get, say, online sampling with pre-computation in less than 1 millisecond. And then even for these higher parameter ranges, you still get online sampling with just a few milliseconds. Yeah, so thank you for your time. Please, I look forward to the virtual conference and seeing everyone there and having answering your questions. Thank you.